All right. Hello, everyone. Okay. Okay, let me share screen. Okay, so in this guest lecture, we'll be continuing the relativity stuff, and I hope you guys understood what I was talking about in the last few guest lectures. Yeah, so in the last guest lecture, I believe we covered Lorentz transformation and space-time interval. So now we're going to move on to some other relativity stuff. So yeah, so first let's move on. So okay, so now we're going to start off with the concept of longitudinal velocity addition. So that is essentially, suppose you are in a frame S, yeah, and there's a frame S prime that's moving with a speed of V2 relative to you. And there's also an object inside S prime that is moving with a speed of V1 relative to S prime. Then we want to know what is the speed of this object relative to you in reference frame S. So if we just look at like classical mechanics with like Galilean relativity, then obviously the speed, let's call the speed of this object in frame S, let's call that u. In Galilean relativity, like in classical mechanics, then u is obviously just equal to v1 plus v2, right? Since you know it's like moving with speed v1 relative to like a frame that is moving with a speed of v2 relative to u. Yeah, so that's the u in classical relativity, but in special relativity, that is no longer the case, obviously. If you look here, you can see what u is equal to. But to derive this, we basically we can just derive this with Lorentz transformation. So suppose that the object inside S prime, like, okay, so suppose that this object inside S prime moves a distance of move the distance of delta x prime during the time of delta t prime relative to S prime. So yeah, so delta x prime and delta t prime are the distance and the time measured within S prime. So like what are the time measured in S prime? So like suppose it moves this distance and this delta x prime distance during a time of delta t prime inside S prime, and then suppose that suppose it moves from like this point to this point. Now, if we look at this object moving from point A to point B in the frame of S, we want, suppose the distance between A and B as measured in the frame of S is delta x, and the time it takes for this object to move from A to B as measured in the frame of S is delta t. Yeah, so then clearly the u here is equal to delta x over delta t, right? Because that's just the definition of velocity. We measure it moving a distance of delta x in the time of delta t. So that is this object velocity. And we also know that v1 is equal to delta x prime over delta t prime, right? This object's velocity as measured with respect to the reference frame S prime. That's just delta x prime over delta t prime, because that's the distance moved in like a certain amount of time as measured in S prime. And we know that the velocity of this object as measured in S prime is V1. And yeah, so here we basically want to find what U is. And well, we can just do Lorentz transformation on this as a review of what the or of what Lorentz transformation says. Yeah, a brief review of what Lorentz transformation is that if we have like the same frames S prime moving with a S prime moving with a velocity of V relative to a frame S, then a distance X, suppose a distance X prime is measured in S prime. This same distance X, suppose a distance of X prime is measured in S prime, then the same distance X is X in like okay, how should I put this? Is a distance of X prime is measured in S prime, then if we transform like this distance X prime into the coordinate frame of S, then into X, then X is equal to X is equal to X prime plus V times delta T prime. And like suppose t prime is the time as measured in S prime, and t, the time as measured in the frame of S, is t prime plus V times X prime over C squared. Yeah. Okay. So so I hope you guys know what the Lorentz transformation is, but yeah. So then if we apply this to this problem, then delta x is the distance measured in S, and delta x prime is the yeah. Oh, by the way, like x and x prime, t and t prime are essentially the distances between two different events as measured in S and S prime. So here the two events are this object going from point A to point B. So the distance between these two events are delta x prime and delta t prime as measured in frame S prime, and delta x and delta t as measured in frame S. So then we can transform delta x and delta t prime into delta x and delta t. This top part is just delta x prime plus v times delta t prime, and this bottom part is delta t prime plus v times delta x prime over c squared, right? Yeah. So then obviously we can just do some algebraic manipulations. We can just get this bottom part we can just get both parts so that they're all in terms of like delta x prime over delta t prime, because as we know from here, v1 is equal to delta x prime over delta t prime. So then we see that this this v is v2, obviously, because it's the speed of the reference frame S prime with respect to reference frame S. So yeah. And yeah, so obviously, since delta x prime over delta t prime is equal to v1, we have v1 plus v2. This u is equal to v1 plus v2 over v1 times v2 over c squared. So as you can see, this is u, same as this equation shown here. So that's just a longitudinal addition, a velocity addition. So if some object is moving with some velocity relative to a frame, which itself is moving with some velocity relative to another frame, then the velocity as measured in like our frame is just this. Are there any questions about this part? No? Okay, then let's move on. So okay. Okay, so let's move on to the relativistic dynamics. So before we had only talked about kinematics, so that was just like yeah, kinematics, that's just like xt and v. So so before we didn't, there were no forces or like momentum or like energy involved, because yeah, yeah. So now we're talking, so now we can talk about what is like dynamics, which includes momentum and energy in relativity. So first, these are the equations for momentum and energy. P is equal to gamma. Well, okay. If we write the momentum and velocity in vector form, then P is equal to gamma times V. So V and P are both vectors here, and gamma is obviously the constant we use so much in relativity. Gamma is 1 over square root 1 minus v squared over c squared. Okay. So for yeah. So as you can see, these equations are like there's a small difference between these equations and the equations in classical mechanics. So let's take a look at how these where these equations came from. So momentum, P equals gamma mv. Okay, technically the equation for momentum, we can do like thought experiments and stuff and think of like a proof for why this P equals gamma mv is a good is like the momentum. But in reality, like if we do these, even if we can do like these proofs of this, but in reality we only know it's true once we experimentally confirm this. So the equations for momentum here and for energy here are all confirmed experimentally. So yeah, but here we're just showing a small thought experiment that shows why this is like a good candidate for the momentum. Well, like a short thought experiment that essentially proves that this equation is that if momentum is equal to gamma mv, then this quantity is conserved in relativity, because both momentum and energy are conserved in relativity as it is in classical mechanics. So this thought experiment essentially proves it's conserved. But if you, so that it shows that it's a good candidate for momentum. But if you really want to show that it actually is the momentum, you have to do experiments and confirm it experimentally. In physics, when you like have like equations like this, you can have like two derivations for why this is true, but you always have to conserve it prove it experimentally. Yeah, so basically. So this thought experiment proves that this quantity is conserved. So imagine if we have two objects, two objects A and B. They're identical, and they are moving towards each other with equal but opposite velocities. So suppose that the velocity of A is like B or something, then B also has the same velocity, except it's in the opposite direction of A. As you can see here, B is moving over towards in this direction, and then at this point, A and B collide. And obviously, since they are identical objects with the same velocity, they will just reflect off each other. And now they'll be moving in opposite directions, but now but as you can see in this diagram, the x component of the velocity of A is opposite, and the same is true for the x component of B's velocity. Yeah, so but their y velocity is still the same because when they collided, they collided like this, so they reflected off each other. Yeah, okay. So any questions about the setup of this experiment? Okay. Okay. So now suppose that suppose that the velocity in the y component of the velocity is Vy and the x component of the velocity is Vx. Now suppose that Vy is very large and Vx is very small. So A and B are only moving at like a slight diagonal, in a slight diagonal. And remember these statements because they're important later. And also suppose that they are colliding on like the plane at which they're colliding, we divide it into like these identical vertical lines. They're all separated by the same distance beneath them. We are essentially using these to like as a clock sort of thing, because suppose A and B are both contain an identical clock, and each clock ticks once the object passes one of these lines. Okay, so yeah, every time A and B passes one of these lines, their clocks tick once. This is also important. Okay, so this is what it looks like from one reference frame. But now if we clearly momentum is conserved in this reference frame. We basically set it up like that. But now if we look at this another reference frame that is moving with a velocity of Vy downwards in the same direction that A is moving. So now, yeah, the velocity of like this frame, if this frame is S and this frame is S prime, then the velocity of this frame of S prime relative to S is Vy downwards. So now, since it's moving along with A, now A no longer has any a y component of the velocity. So it only has it's only moving in the x direction. But B, since B was moving in the opposite direction of A, it still has a y component to the velocity moving upwards. Yeah. So then, okay. So then let's look at how momentum could be conserved in like this scenario. So okay, so suppose that B is moving with a very large with a very high velocity v. Okay, let's just call it this v. V is moving with a very large velocity of v. Then okay. Okay, so now, but so then if we look at the components of their momentums in the x direction, since momentum like still has to be conserved, the momentum in the x direction still has to be equal for both A and B. So both of their momentums in the x direction have to be px. And yeah. So okay. Now, but if we look at their velocities in the x direction, the x components of their velocities are no longer equal now, because let's say the velocity of A in the x direction is still vx, but now B, since it is moving at a very high speed, at a very high and vx is very small, but since B is moving at a very high speed, now the clock on B is now ticking a lot slower. It's now ticking at a rate of it's ticking slower by a factor of 1 over gamma relative to A. Why is this 1 over gamma relative to A? Because now B is moving much faster than A. A has a very low velocity, but B has a very high velocity. So it has a slower clock. But as we said before, the clocks tick every time this object moves past the vertical line. So now B has to have a slower velocity now, slower horizontal velocity now, because its clock is ticking slower. So in this frame, B has a slower horizontal velocity. The difference is Vx over gamma. Like, yeah, this is B's horizontal velocity, Vx over gamma, while A's horizontal velocity is Vx. So if we just look at the old Newtonian definition of momentum, that is P equals mv. Well, obviously we need Px for both A and B to be equal in order for momentum to be conserved in like this system. So, but if we take Px equals mv, P equals mv, then Px equals mvx for A, while for B, the B's momentum will be mvx over gamma. Clearly, these are not the same. So obviously, the old Newtonian definition of momentum cannot work in a relativistic like world. So, but if we take this definition, P equals gamma mv. Okay. P equals gamma mv. Well, now if we look at pxa, that's just well, the gamma for A, well, this gamma is like for A, the velocity for A is 1 over square root 1 over Vx squared over C squared. But as we noted earlier, A's velocity is very small. So the gamma for A is essentially equal to 1. So Pxa is basically just approximates to mvx. On the other hand, for Pxb, if we take P is equal to gamma times mv, the gamma for P cancels out with this. So Pxb will also be equal to mvx if we take this definition of P. So as we can see, if we take this definition, P equals gamma mv, then the momentum is indeed conserved in a relativistic system. Now, technically, this doesn't mean that the momentum is indeed equal to gamma mv. Although if we look at this, like, although we know that this p equals gamma mv could be the momentum, but it doesn't really, this experiment doesn't really show that p equals gamma mv is actually the momentum in relativity. To show that, you have to prove it with with experiments, but it does show that the quantity p equals gamma mv is conserved. So so yeah, this was just an interesting, very classical thought experiment to demonstrate like why this could be the momentum. So yeah, okay, so if we go back to, okay, so are there any questions about this? Okay then. Okay, so let's go back to dynamics. As we said, so P equals gamma mv and E equals gamma mc squared. Well, that's the momentum and total energy of a relativistic particle. And yeah, and it's okay. Yeah. And obviously they can be shown with experiment. You can show that E equals gamma mc squared is also conserved in like a sort of a similar experiment. So we won't go into here. Now E squared equals P, another important equation is E squared equals P squared C squared plus M squared C to the fourth. This, you can just basically plug in E equals gamma mc squared and P equals gamma mv into this equation. Like, yeah, just plug in P equals gamma mv and E equals gamma mc squared. And you can show that this equation is true. This is also an important equation and it's pretty useful sometimes. Yeah, so these are like the important equations to remember. And also, suppose that the velocity of an object is equal to 0, so it's not moving. Then the equation for energy just become, since if the velocity is 0, then gamma is just 1. So this just becomes the famous E equals mc squared equation. That's the rest energy of the like a part of a relativistic, well, just the rest energy of a particle. So yeah, okay, and also note that, okay, another interesting result of E equals gamma mc squared is, suppose that, okay, let's first write this out. E equals gamma mc squared is just mc squared over square root 1 minus v squared over c squared. Now suppose that v is much smaller than c. Yeah, so then we can take the 1 over square root 1 minus v squared over c squared, and we can do binomial expansion on this quantity, since that's just 1 minus v squared over c squared to the 1/2. And we will get something like 1 plus 1/2 times v squared over c squared plus some other quantities. But for all those, okay, mc squared. But for all of those other quantities, they'll be at a higher power of v squared over c squared. Like the power of v squared over c squared will be to the second or third and so on power. Now, if we assume that v is a lot smaller than c, then all those other quantities basically go to 0. So we can only care about the first two quantities here if v is a lot smaller than c. Then if we expand this, we just get that this is equal to 1/2 mc squared plus 1/2 mv squared. And obviously the quantities in the later in the binomial expansion, we don't really care about because they go to 0 because of higher power, you know. So this part on the left, mc squared, that is just the rest energy of a particle. This part here, 1/2 mv squared, that should be an equation that's very familiar to everyone. 1/2 mv squared is just the kinetic energy of an equation of a particle. So as we can see, if v is a lot smaller than c, then this equation E for total energy of a particle reduces to mc squared plus the kinetic energy of a particle. So in classical mechanics, so the equation of E equals gamma mc squared is one that holds very well. Is one that is like very it's like, if we take the classical limit of relativity, then this relativistic equation just reduces to classical mechanics relations. So this equation in classical mechanics are like, what's it called? Basically, the limit of relativity in classical mechanics just reduces to like the classical mechanics we all know. So that's pretty cool. And it's further indication that this equation is probably correct. And force in relativity, you may know that force is equal to F equals ma, but this isn't true in relativity. This is only true in the limit of classical mechanics. Force in relativity is just F equals dp over dt. That is the derivative of momentum. So this equation still holds true in relativity. So yeah, if you have to find the force on a particle, it's just F equals dp over dt. Are there any questions? Okay, so I believe that I'm out of time and like material. So the next lecture can go now. Thank you for listening. If there aren't any more questions.